Hi guys, we are jumping into chapter 9, which deals with transformations. Transformations are different types of changes to figures in a three-dimensional zone. So there's going to be lots of different types. There's translations, which are slides, there's reflections, there's rotations, all that good stuff. So we're going to start with 9.1, which deals with translations. So let's see, today's the 4th. By the time we're done today, you should be able to identify rigid motions and find translation images of figures. So a transformation in general is the term that encapsulates all the different types of transformations, including translations, slides, flips, all that good stuff. So a transformation, generally speaking, is a function or mapping that changes the position, shape, or size of a figure. So we're going to do something. We're either going to move it, we're going to stretch it, we're going to make it bigger, we're going to make it smaller, we're going to leave it the same and just rotate it around. So it's a transformation, it's just a change in the original figure. So let's take a look at some of these dominoes. So if I had a domino upside down and I flipped the domino over, that's a type of transformation. This is actually going to be a reflection on or in a specific line of reflection. We'll take a look at that later in the week. I also can take and slide the domino without changing anything else about it, just move it to a new position. So slides or moves are called translations. So we're going to look at those today. And then if I turn it so that I change its position, its look within the original setting, those turns or twists or what else you call them? Lots of different things. But these are going to be called rotations. And there's different ways to rotate. So later in the week, for rotations, you will need to have a compass and a protractor at home. So make sure you have one of those available and with you when we get to rotations. All right. When we're talking about transformations, we have to identify the original. So here's what it will look like originally. This is called a pre-image. That's the fancy geometry term for the original position and look of the figure. And then after we do a transformation, we end up with an image. So I think of image after, image after. That's what sticks in my head. Image after, image after. So in a transformation, which can be any type of transformation, reflections, translations, rotations, the original figure is the pre-image. The resulting figure is your image. So we just got to get used to the terminology there. We'll keep working with it so it'll stick a little bit. A transformation preserves distance and angle measures. In other words, the figure stays the same shape and size. So we're not doing any dilations, which are shrinking or growing our things. We're doing transformation. So my size and my general shape stays the same. I'm just moving it around. These are called rigid motion or isometry. That's what it means when I do a transformation that does not change the look of the figure. So if I start with a pre-image that is a box, this is my pre-image, so it was my original, and I transformed it or changed it into the image, if I can spell right, M-A-G-E, image, I want to know, is this a rigid motion? Did I preserve the distance between each of the points and the angle measures. So clearly not rigid motion, because I changed the distance between this point and this point became a much longer distance. I can look at this next one. I have a pre-image and an image. I don't have the same orientation because it's flipped over, but is it a rigid motion? Is the distance between this point and this point the same with my image? Is the distance between this point and this point the same as the distance between its corresponding side length? And it is. So this is an isometry, aka rigid motion. So you're going to see both those terms. You need to be able to understand that. So specifically speaking, though, if I'm looking at this image and pre-image, this is specifically a reflection. I flipped it over that line, which changed its orientation. So we'll talk about that a little bit later. And then I take a look. If I need to get out a ruler, or if I'm in a coordinate plane, I can use a distance formula to make sure that the distance between this point and this point stayed the same, and that my angle measures, so I can check my slopes to make sure all my angle measures stay the same. So this, yes, rigid motion. There's another way to take a look at and see if you have a rigid motion or an isometry, is to look between the pre-image point and its corresponding image point. This distance, which is known also as a vector, between its pre-image and the image, every single point should end up being the same length. So we originally said, yeah, this is definitely a rigid motion. But what happens when I look at it this way? Did I preserve the same shape and size? So we're going to take a look at this in a little bit and figure out if this is really true, if it's not, what happened with my vector distances. So let's take a look. Generally speaking, we're going to come back to this one, okay? So a transformation, which again encompasses reflections, translation, and rotations, maps or identifies every point of a figure onto its image. So this dealt with why it was a function when we were taking a look at this in geometry or in algebra last year. Functions mean there's a one-to-one relationship for every single point in that figure. So we want to take a look at transformations, specifically translations, and how to determine what's going on. So we know that images and their corresponding points. So prime, this word prime, you're going to see prime a lot. Prime is used to identify, the image or image actor is what I keep thinking. So if I'm taking a look at triangle JKQ, it maps every single point on JKQ to its image, which is known as triangle J prime, K prime, Q prime. Prime is that little hash mark that goes behind it. So if I were looking at just this, I would know that I had a regular old triangle JKQ and I did some sort of transformation that got me to the prime of each of those points. This little arrow here means maps to. Just as we were doing with corresponding or congruent or similar triangles, corresponding parts still need to be lined up just like we always have. So if I want to identify the transformation here, I talk about E, F, G, and H. Maps to E prime, F prime, G prime, H prime. So you could also say angle F prime is image of, because image after, so f prime is after, the image of angle f. You could say that about each of the angles. You could say that EF, if I'm looking at just segment EF, it maps to its image or prime segment E prime F prime. Triangle, well, that should be a D. NID maps to triangle SUP. So prime is not always used, but we tend to use prime so that we can make sure that we realize that it is mapping to a specific one to the other. So let's take a look at translating stuff. So that was just general vocabulary for the whole chapter 9. Let's get into specific types of transformations. Today we're going to look at translation. So a translation is a transformation that maps all points the same distance and in the same direction. So for a translation, I take my original triangle and I map it in the same distance and the same direction. So when I am looking at this figure here, I know that I mapped it the same direction because B to B prime segment has to be equal to A prime segment as it is to C prime. That way it maps the same distance and all the slopes are equal. Same direction. So we know that all of these are congruent to get me to my new image triangle A prime, B prime, C prime. These arrows here are vectors. And in vectors, which I think you know from science, vectors give you direction, tells you where you're going, and magnitude. And magnitude is just the fancy word for distance, how far, what's the length of. So we can identify the translation here as triangle ABC maps to triangle A prime, B prime, C prime. It maps to. When we are identifying a translation, a specific translation, we use a capital T. So my notation for a translation is a capital T. Okay? So what we take a look at is when we are doing vector notation. This is a mapping. If I want to specifically identify the translation, it's called a function notation. We say, hey, it was a translation for the vector 4, -2 of, we're looking at this figure right now, A, B, C, D onto A prime, B prime, C prime, D prime. This is my rule, and this is my full translation statement. So let's figure out where these numbers come from. So when we're looking at a vector, we are in a coordinate plane, and a vector is going to give me a mapping x, y onto some sort of x plus or minus, comma, y plus or minus. So let's take a look at this specifically. So there are no primes on these letters, so this must have been my pre-image. I moved or translated my pre-image into my prime ABCD. So this is my image. And what the vector does, image, what the vector does is it tells me how I moved it. So I need to take one of the points, because if I do it for one, that means I did it for all of them, and figure out what my moves were. B moved from here to here. I moved 1, 2, 3, 4 places to the right. Moves 4 units right. So that is a +4 in my x coordinate point. And from there I moved 1, 2 down, which means a -2 for my y. This is my x change in x. This is my change in y. So let's try some. It's easier to understand once we get them in there. All right, draw triangle PQR with vertices at the given vertices. Find the image, that means after, of each vertex after the translation. So this is my mapping notation. Graph the image. So we need to start by first graphing our original pre-image, PQR. So we've got P at 4, 2. 1, 2, 3, 4, 1, 2. So that's P. We've got Q at 6, 2. 1, 2, 3, 4, 5, 6, 2. That's Q. And I've got R at 1, 2, 3, 4, -2. 1, 2. R. That is my original pre-image triangle PQR. The mapping tells me what I'm going to do with each of the coordinate points to give me my prime coordinates. I'm going to set it up the long way. Once we do a long way a couple times, if you've got the process, you no longer need to do it this way. But we start with our map, and it tells us, hey, for every x, y, we map it such that x -4 and y +1. That means every x coordinate gets 4 taken away, and every y coordinate adds 1. So in my original, P is 4, 2, Q is 6, 2, and R is 4, -2. That just came directly from my original pre-image. I map it by subtracting 4 from every x. So I end up with P prime, Q prime, and R prime by x, which is my original x is 4, -4, comma, my original y, 2, +1. Q prime starts with 6, so my original x -4, comma, my original y is 2, +1. My original x is 4 minus my 4, and my original y is -2 +1, which is equal to my 4 minus 4 is 0, 2 plus 1 is 3, 6 minus 4 is 2, 2 plus 1 is 3, and I get 0 minus 1. Those are my new image points, so I'm going to go graph those points. So P prime is 0, 1, 2, 3. That's my new P prime. Q prime is 2, 1, 2, 1, 2, 3. Q prime. And R prime is 0, -1. My image should be the same exact shape, only shifted. So same shape, and I should get P P prime equal to Q prime bubbles is equal to R prime. Meaning that the segments between, I'm going to bust out a ruler here, P and P prime should be congruent to Q and Q prime, should be congruent to R and R prime. Make sure I mark that R prime. This was my original pre-image. This becomes my image. These should all be the same distance, so I'm going to mark those all congruent. So if I wanted to prove that this was a translation, then I would show that all the sections between the new image and the old image, all the vertices, are the same length. Okay, we're good? Okay, so we also sometimes see it looking in function notation. It's the same exact thing, only it just writes it in a different way. It's not in prime notation, it's in function notation. So that we should be able to quickly kind of take a look and graph some of this stuff without having to do all the work. So if I want to take a look at example 5, without cranking out the numbers, can I list all my PQR, then show all this work to show that I am doing some transformation stuff, and then get my new PQ, P prime, Q prime, R prime? You bet. This method will always work. But what this tells me in function notation is the capital T, that means translate. So we should just see a movement, no rotation, no shrinking, no flipping, any of that. And then this vector, -2, -5, is an XY. That vector means -2 means left, because that's my change in my X and the change in my Y. So left is the -2. -5 implies negative, which means down, because my Y, change in Y is an up and down, 5. So if I were to give you an original triangle at, so let's call it 2, 1, 1, 2, 1. Call that P. Then 3, 3. 1, 2, 3, 1, 2, 3. That's Q. And let's say R is at -1, 1, 2, 3. So if this is my pre-image, and this was my translation function, I should be able to know that every single point is going to go left 2 and down 5. So if I start at over here, which happens to be R, doesn't matter where you start, I go left 2 and down 5. So here's 1, 2, 1, 2, 3, 4, 5. That's where my new R prime should be. Q, left 2, 1, 2, down 5. 1, 2, 3, 4, 5. That's my image, so it's Q prime. Left 2, 1, 2, 1, 2, 3, 4, and I didn't give you enough lines, so we'll just call that P prime back there. I should end up with a triangle that is exactly the same shape, just shifted left 2 and down 5. This becomes my image. We good? If we cannot use this method, or if you're told to specifically list out your mapping, you have that method as well. Okay, so you have the next 3 to try. I would like this first one to be mapped out, so show all the mapping, A mapping to A prime, then show what's going on. And then you can choose if you want to use your graphing method or the mapping method after that. So go ahead and pause your video, work on those 3, and then come back, check your answers. Okay, on the first one, your original pre-image is graphed up here. Your image or your second translated figure should be end up down here. You should have corresponding lines that have the same slope as the pre-image. You should have angles that are the same. Everything should be the same. It was just shifted over. And this is the work you need to at least show when I'm asking you to do the mapping. On the next 2, you should have your triangles that are shifted and look like that. So pause the video if you did not get these, check your answers, make sure you're in the same spot. So remember, translations, I'm looking for the same exact orientation, the same exact isometry, because nothing changed, and it's just shifted. There's no change in slopes, no change in anything. Alright, so let's finish this up. Alright, so we're going to now just do the opposite of what we were doing before. We were given some figures, then we translated it based on a mapping or a function rule. Now we're going to go backwards. Now we're going to write a rule based on what we're given. So we're going to use the graphs to do this. It's pretty easy. So this first one we take a look at. This must be my pre-image because there's no primes on it. So this is my pre. So that means I went from this image to the P prime, Q prime, R prime, S prime. I need to pick one point and figure out what happened to write my translation rule. So let's take a look. So I'm going to use P because up here at the top and it's easy. I went, so we go left, right first. 1, 2, 3, 4, 5, 6, 7, 8. So this is 8 right. So that's going to be a plus 8. Then from that point, I went 1, 2 down. 2 down. So this is 8 right. And 2 down. So 2 down means minus 2. Which means D's hanging out. So now I already have my function rule. I know that I translated it. I just shifted it. I moved it around, so it's a translation. With the vector, x comes first, 8 down 2 of the original PQRS figure. So that is my rule. Simple, simple. This one says the translation image is at. So they didn't graph the image for us. They gave us the pre-image, so we can go figure out what the points are in the pre-image and how we got to the image. So pick a point, so just like this, pick one point and find change in X and change in Y. Okay? Same thing here. So I'm going to use L. Doesn't matter which point you pick. I know that L is at -6, -1. It was mapped onto L prime that they told me was 1, -2. So how did I go from -6 to -6 to the new X of 1 and -1 to -2? So -6 to get up to 1, I must have added 7, so that's the change in my X. -1 to get to -2, I must have taken away another 1, that's the change in my Y. My translation rule then is it was a translation of the vector, X comes first, 7, -1 of the figure triangle LMN. Once I check one point, I don't need to go check the other points for my rule. Just be real careful to make sure you get those right. Okay, pause the video once again. Do the next. Alright, there's what I got for your practice problem. Your rule is a translation of the vector -3, 2 of triangle ABC onto triangle A prime, B prime, C prime. In order to prove it's a rigid motion, or i.e. a isometry, you need to find the lengths and the slopes of all three sides in both triangle ABC and triangle A prime, B prime, C prime. All the corresponding stuff should have the same slope, same side length. Okay, if you did not get those right, make sure you circle them so we can talk about them tomorrow. And the last piece of information deals with compositions. So compositions of translations are pretty basic. A composition of any two or more translations is just another translation. So what we're talking about is if this Joe Schmo here, 3, she can shoot the ball or whatever the heck they're playing over there directly to 5, or she can shoot it to 9, who then shoots it to 5. This piece here would be a composition. We end up in the same spot, in the same translation spot. We've just composed 2 different ways to get there. So we'll work on these a little bit more. The other types of compositions get a little more tricky. Order of operations kicks in, but for now it's pretty easy. So in the diagram shows 2 moves of the black bishop. So the black bishop started here. It's hard to see in the printout. And where's the bishop in relation to its original position? So those of us who don't play chess and can identify whether this is G2 or whatever that cell is, then we need to identify the original position. So we're going to let 0, 0 be original position. Okay, since we're practicing compositions, we know by looking at the graph or the chess piece that eventually if they move here and then move here, ultimately we know it should be how far left and right and how far down. 1, 2, 3, 4, 5, 6. A translation of 6 to the right, so it's positive, and down to -2. Okay, so we know that that's what we should get. So let's practice the translation so you know how to do them when it's not this easy. So my first translation is what? I went from here to here. So I went 1, 2, 1, 2, 3, 4, because this is where I'm at. 4 to the right, so we know it's a +4, and I went down 1, 2, 3, 4, down 4. So that's the translation of the starting point of 0, 0. So we know that the next point would be technically 4, -4. The second translation from 4, oops, it should be a vector, 4 from, we got to figure out where it's from first. So we got to figure out our vector. From 4, -4, 2. So let's find out what our vector was. We went right 2, because we ended up here, and then up 2. So our translation is 2, 2. Of this position, because this position was where we're at when we started our second translation, so we end up at 6, -2. So the bishop is 6 squares down, nope, 6 squares right, and 2 squares down, which is what we originally thought when we just skipped over the composition. So you're going to start with this position here, practice real quick this translation move here, and then you'll be all done. And I'll see you in class. Okay, bye.